Tutorial number 28 with drill 22, and we're going to be discussing frequency modulation. Frequency modulation is the simplest and easiest way of producing a transmitter and receiver, although double sideband is pretty simple as well. I've left frequency modulation till now because we've done DSB and SSB and we're receivers and transmitters, and we've got a good idea of the super heterodyne principle. For FM, for the standard, we only need to know a few basic things about FM and the identification of the stages in an FM transmitter and receiver. This slide is a simple FM transmitter. FM is really easy to produce, but before I talk about the simple transmitter, I just want to remind you that we've done double sideband and single sideband, and what we're doing there is changing the amplitude of the transmitted signal. So we've got our modulating audio, the voice coming from the microphone, and in double sideband and single sideband, our voice is changing the power, the total amplitude of the signal that we're transmitting, and when we receive it, we get those power variations and we convert them back into audio so that we can hear it. There's another way of putting information on an electromagnetic wave, and that is to get our voice to change the frequency of the wave, and therefore the frequency, not the amplitude of the wave, is going to hold the modulation that we want to transmit. In the receiver, we need something to take the changes in frequency and convert them back to audio frequencies. So FM is modulating an electromagnetic wave in such a way that our modulation causes the frequency of the carrier wave to vary, and in the receiver we have to convert those changes in the frequency of the carrier wave back to audio. It's a fairly simple process, and you'll understand most of the rest of a FM receiver and transmitter because it's the same for SSB and single sideband. FM is a wider bandwidth. FM for amateur bands is about 16 kilohertz, so all of the IF amplifiers and filters in an FM transmitter and receiver are wider than double sideband and single sideband. Single sideband is 3 kilohertz, double sideband is 6 kilohertz, and normal FM for amateur radio communications is about 16 kilohertz. The way that's done in an amateur transceiver is you have to buy a filter for your IF amplifier normally. Amateur radio transceivers come with double sideband, single sideband and FM, but they are normally only fitted with a single sideband filter at 6 kilohertz. If you're going to be using a lot of FM on HF, and you can't use 16 kilohertz on HF, you have to use a narrower bandwidth, then you're going to need, to get the full benefits of FM, you're going to need an FM crystal filter for your IF amplifier. Okay, let's have a look at how easy it is to make a frequency modulated signal. Right, let's look at this simple FM transmitter. What we have is an oscillator, and the frequency of operation of this oscillator is determined by this LC circuit. Suppose we could change the resonant frequency of that LC circuit with our voice. Well, we can. Suppose this capacitor, or part of this capacitor, is a capacitor microphone. When we speak into the capacitor microphone, its capacitance changes, and therefore the resonant frequency of this circuit changes. For example, suppose the oscillator was, without speech in the microphone, oscillating on 1 megahertz. So with no speech in the microphone, we've got a 1 megahertz carrier wave being transmitted and nothing else. It doesn't change in amplitude, it doesn't change in frequency. When we speak into the microphone, we change the resonant frequency of this circuit depending upon the amplitude of our voice. If our voice is very loud, we'll change the capacitance of the microphone greatly, and there will be a great deviation in the oscillator's frequency. If we speak softly, there will be a small deviation in the oscillator's frequency. A little transmitter such as this could be used in a cordless microphone, a wireless microphone, or a FM bug, the sort of kit thing you buy for a cordless mic or a little FM transmitter. This is actually a practical transmitter. This one would drift in frequency because an LC circuit is not very stable, but it would work nevertheless. It's a very, very simple circuit, about 10 components to build a simple FM transmitter. So when we speak into the microphone, the frequency varies according to the amplitude of our voice. If we were to look at that on an oscilloscope, and remember on an oscilloscope we have time on the horizontal axes. So we're going to be looking at sine waves, radio frequency sine waves, and the vertical axis is the amplitude of the sine waves. Now because I'm such a bad drawer, I'll probably make changes in amplitude. So I'm going to draw a couple of lines to help me. So without any modulation, we've simply got a sine wave on 1 megahertz. If we talk into the microphone, the frequency changes. It may decrease for a moment and then it will increase. Frequency gets higher. We have more cycles per second. And then the next instant it will decrease again. So there are frequency variations but no amplitude. The amplitude does not change. There is no change in the amplitude of the signal, whereas in double sideband and single sideband we're relying on the changes in amplitude to transfer our information. With frequency modulation we're relying on changes in frequency to convey the information to the receiver, and that has some very distinct advantages, particularly in terms of noise and clarity. But it also has some disadvantages for HF because the bandwidth of an FM signal on amateur frequencies is about 16 kilohertz. And 16 kilohertz is a pretty broad signal to put on HF bands. So generally, and I have to say generally because we do use FM on HF, generally FM is more suited to VHF and above because of its wider bandwidth. If we do use FM on HF bands, we have to reduce its bandwidth to a much lower bandwidth by regulation. The simple FM transmitter that we just had up would work. The problem is LC circuits aren't very stable. What is stable is a crystal oscillator. I haven't drawn the crystal oscillator, it would be here. So here would be the circuit of a crystal oscillator. What I've done is just shown the crystal of the crystal oscillator. And in series with the crystal we've put a varactor diode. And a varactor diode changes its capacitance when we change the voltage across it. And if we put a capacitance in series with a crystal and vary that capacitance, then the frequency of the crystal will vary slightly. This is how we produce FM. I know it looks like a very simple diagram, but this is actually how we produce FM in a modern amateur radio transceiver. What we're doing is taking the voice from our microphone, amplifying it. We've got an inductor here, a choke, and that's just to stop the radio frequency. You won't be assessed on this. That choke is just to stop the radio frequencies going into the audio amplifier. audio stages and RF stages should be isolated from each other, and that's what that's doing there. That's an RF choke, so don't worry too much about that. The important thing is voice in the microphone, voice frequencies here. This is audio frequencies, and they're changing in amplitude. If you yell, you get a really loud one. If you talk softly, it goes down. So it's changing in amplitude, so that's a changing voltage. That's applied to the varactor diode. That changing voltage changes the capacitance of the varactor diode, and because it's in series with the crystal, that's going to change the frequency of the crystal according to our modulation. So we're going to get a radio frequency output which changes in frequency and does not change in amplitude. So I know I'm changing in amplitude there because I just can't draw that well. So the amplitude is constant and the frequency changes. There are frequency changes and the amplitude is constant because the information now, our modulation, is in the amplitude of the carrier wave. Our information is now in the frequency of the carrier wave, and we're not relying on any amplitude changes to convey any information. That's what FM is. How much the frequency varies with the modulating audio, because the frequency of the crystal is going to go up and down, up and down, up and down, back and forth around the carrier frequency. So if the carrier was 1 megahertz, that's without any voice, with no modulation, we're just transmitting a 1 megahertz carrier. And when we start speaking into the mic, the frequency of the crystal varies up and down around 1 megahertz to a bandwidth on amateur bands of about 16 kilohertz. Bandwidth on FM is a little bit complex to calculate, so we're not going to go there. You don't need to know it for your standard license. The maximum amount that the crystal varies in frequency is called the peak deviation, and you do need to know that. So we're applying audio to the varactor, changing its capacitance, which is changing the oscillation frequency of the crystal, and the maximum amount of change of deviation is called in frequency is called the peak deviation. Let's have a look at a practical diagram of an FM transmitter and receiver. This slide is a simplified block diagram of an FM transmitter. I'll just tell you why it's simplified. We're doing a frequency conversion here. Every time we have a mixer and an oscillator, we're doing a frequency conversion, and that would normally be followed by an IF amplifier, and it could be a double conversion transmitter, so that could go to another mixer and another frequency converter. So really the discussion of that area onwards is irrelevant for FM, except for the bandwidth, which is wider, 16 kilohertz as compared to 3 and 6 for amplitude modulation. So really it's just this part of the transmitter we're interested in, because when we discussed double sideband and single sideband, we talked about having buffers here, we talked about having another frequency converter, and I've lumped the power amplifier chain, which would normally be a pre-driver, a driver and a power amplifier. I've just lumped that into one because we've covered all of that and there's no need to go back to it. This is just a frequency changer to put us on the frequency that we want to transmit on, and this is just an amplifier to boost the signal to a high power. So there's no need for us to discuss that part of the circuit, and I've simplified it right down to its essentials. However, the first three stages are the stages that we just looked at in the previous slide. We've got a microphone amplifier, and we've got that varactor diode in series with a crystal which is part of this oscillator. So when we speak into the microphone, this oscillator could be on 1 megahertz or 20 megahertz, and as when we speak into the microphone, the audio voltages from our voice act upon the varactor diode and make the crystal of this oscillator deviate back and forwards around its center frequency, and that produces FM. So the new term you've learned is reactance modulator. And all that is what we had up there before, simply a crystal, very stable oscillator, which is part of this oscillator, and in series with that we have a varactor diode, and our audio, we put a radio frequency choke, I told you why that was there, goes to there. So that's what the reactance modulator is, and that crystal is part of that oscillator, and that's how we produce FM. It's as simple as that. The amplitude of the signal in FM is constant, and the frequency of the signal varies with the degree of modulation. It's the amplitude of our voice which is determining the deviation around the center frequency of our FM signal. Now I've put the receiver up for FM. Thought it might be helpful to leave the transmitter there. We're making our FM in that section there. We're not really interested in that. We've discussed it. That could be very similar to the block diagram that I gave you on a single sideband transceiver from that point on. Here is a simplified diagram of an FM receiver, and up until this point nothing has changed. That's you should be very familiar with from our discussion of double sideband and single sideband. RF amplifier amplifies the incoming signal. It's a super heterodyne receiver, so we're changing the frequency of the incoming signal to an intermediate frequency. So that's all pretty much the same as any other receiver, the same as this section here in the transmitter. The difference with FM is that the bandwidth of the IF amplifiers would have to be wider because FM is 16 kilohertz wide. So we get to the limiter. The limiter, remember before I said that the information is conveyed in the frequency changes of the signal and not the amplitude changes? Well, a lot of noise, man-made noise and cosmic noise, causes the amplitude of our signal to vary. So instead of our signal being square top and bottom, just give myself a couple of guidelines here. That's the amplitude of the signal, those two top lines. So theoretically, because we're only changing the frequency, our radio frequency sine wave will get higher in frequency and lower in frequency, but theoretically it should not change in amplitude. In practice it does. There might be a bit of noise, a noise spike here, another noise spike here, then there's no noise. And so any change in amplitude of our FM signal is noise. And what the limiter does is slice off the top and bottom of the signal. And we can do that because we're not interested in amplitude changes. If we have any amplitude changes, they are due to noise. We're only interested in frequency changes. So the function of the limiter is to remove amplitude variations in the signal. It's a very simple amplifier, and it is driven to a point where it can't amplify very high signals or very low signals, and it slices off the top and bottom of the signal. But the signal's frequency changes remains unchanged. And so that gets rid of a lot of noise from us. What radio amateurs say sometimes when they're having a conversation, it gets rid of noise. You might hear a radio amateur say, "What's my signal like?" And the chap will respond, "You have full limiter action." It's a good signal, you've got full limiting. And when you've got full limiting, that means you've got a strong signal, and the limiter is able to eliminate all the amplitude variations, and it is the amplitude variations that are the noise in the receiver. That's why FM is so clear. One of the reasons, the main reason why FM is so clear. So there's only two stages so far that are new to you. One is the limiter, and it removes amplitude variations. The next stage is the demodulator in an FM receiver. Demodulators, all demodulators, convert radio frequency signals back into audio signals. The demodulator in a FM receiver has to convert changes in frequency back into changes of voltage. Remember, in our transmitter, we were speaking into the microphone and we produced an audio signal which we amplified, so we had changes of voltage. We converted the change in our voice to changes in voltage, and we used those changes in voltage to control the capacitance of a capacitor, which varied the frequency of this oscillator. So the discriminator's job then is to convert changes in frequency back to changes in voltage, and those changes in voltage are the same ones that went into the microphone. So there we've got demodulation. Here we've got changes in voltage in our voice, and that caused changes in frequency to be transmitted. We received it, we converted it to an IF, we removed the amplitude variations, and then we then go into the discriminator, and the discriminator converts changes in frequency. I'll try and draw some frequency changes here. It's a bit hard. So they're and it's had its amplitude squared off like that by the limiter. Now we've got changes in frequency, and the discriminator converts that to changes in voltage, which is the same changes in voltage that went into our microphone. The only thing to do then is to amplify it and drive a loudspeaker. There are a couple of simple circuits in the audio amplifier and the micro amplifier called de-emphasis and pre-emphasis, but we don't need to go there for the standard assessment. But they're very simple circuits. There are a couple of components, so don't feel like you're being shortchanged. You're not. I just don't want to extend the course longer than is needed for you. Well, that's about all we need to cover for FM for the standard license, and the reason why it's so quick is because there isn't a lot of difference between a super heterodyne transmitter and receiver for FM than there is for AM or DSB, and we've covered them very thoroughly. You've really only got two new stages to worry about in the FM transmitter, and actually one stage, the reactance modulator. And in the receiver, you've only got two stages to worry about, and that's the limiter and discriminator, which is the demodulator, and the limiter removes amplitude variations. So I'm just going to clear my screen so that you can look at that a little bit more clearly. You might want to print that, just screen grab it and print it, use it for reference, because I think it's time. There aren't an awful lot of questions on FM, and I think the most appropriate thing for us to do now is to go through some of those questions, because there's really just no need for us to go much deeper into the theory. And there isn't an awful lot more theory, just maybe a bit of mathematics, because an FM signal is rather complicated to describe mathematically. So I'll see you shortly, and we'll have a go at some trial exam questions that are plausible on frequency modulation. Well, we're back, and we're not doing the exam questions just yet, because in the interim I was looking at the advanced course notes, and I found this diagram of frequency modulation from the advanced course. Let me explain how this is the modulating audio. This is the audio we're applying to the varactor diode in the carrier oscillator. This is the carrier oscillator unmodulated, so this is without any voice at all. So an FM transmitter just transmits a radio frequency carrier. Notice there's no changes in amplitude. And then when we apply the modulating audio to the reactance modulator, the bottom diagram shows us how the carrier is changing in frequency. This is a lower frequency here because there's less cycles per second. Here they're bunched up, there's more cycles per second, and so on. So it's changes in audio amplitude controlling the frequency of the transmitted signal. That's FM. I just thought that would be beneficial, particularly in the light of my fairly pathetic drawing skills. And now we'll go through some trial questions. Let's have a look at some questions of the type that you may get. Not a lot of questions on FM, because you've really learnt a lot about receivers and transmitters when we've done double sideband and single sideband. Your drill for this tutorial is drill number 22. 22.1. The stage used to modulate an FM transmitter is the reactance modulator. 22.2. In this block diagram of an FM transmitter, the block marked X is the oscillator. The reactance modulator is what makes the oscillator change in frequency with the modulating audio, so that is the oscillator. 22.3. In this block diagram of an FM transmitter, the block marked X, again, that's the, well, not again, what was the last one? Now that was the oscillator, and now they're asking for the reactance modulator, which is basically just a crystal with a quartz crystal with a bractodiode in series with it. And the audio amplifier superimposes the audio voltage on the bracta, causing the bracta to change capacitance, causing this oscillator to change in frequency, and thereby generating frequency modulation. 22.4. With frequency modulation, the maximum shift in the carrier frequency with modulation is called peak deviation. The deviation is the amount by which the carrier changes frequency around its center frequency when it's unmodulated. The maximum amount of change of that frequency is called the peak deviation. 22.5. In an FM signal, the power in the signal, I'll have to read this, the power in the signal varies with modulation. That's not true. The bandwidth is constant regardless of the modulating frequency. That's not true. The bandwidth decreases as the modulating frequency increases. That's not true. The signal amplitude remains constant. There's no change in amplitude in an FM signal with modulation. If there is any change in amplitude, it occurs after the signal leaves the transmitter, and that's noise, and in the receiver that noise is removed from the amplitude of the signal by a limiter. When we get noise on an AM signal, we can't remove it because the information, the intelligence, is in the noise. So that's the advantage of FM. Most noise is amplitude modulated, and we can remove that noise in a FM receiver. 22.6. The bandwidth of an FM signal is determined by the amplitude of the modulating audio, how loud you speak into the microphone. With double sideband and single sideband, the bandwidth of the signal is determined by the highest frequency of the modulating audio. I'll say that again. In double sideband and single sideband and all amplitude modulation, the bandwidth of the signal is determined by the highest frequency of the modulating audio. Highest modulating audio used in amateur radio is 3 kHz. That means the bandwidth of SSB is 3 kHz and double sideband is 6 kHz. It's the frequency of your voice which determines the bandwidth in AM. In FM, it is the amplitude of the modulating audio that determines the bandwidth. 22.7. The stage that removes unwanted amplitude variations, in brackets noise, in an FM receiver is called the limiter. Oops. There we go. 22.8. The demodulator in an FM receiver is called the discriminator. There are different types of discriminator, but you don't need to know about them. A discriminator is a global name for an FM demodulator. 22.9. The amplitude of an FM signal varies with modulation. Now that's nonsense, remains constant. And I think that's it. Yes. That's it. That's the end of this tutorial. I hope it made sense to you. If it doesn't, tell me. Send me an email and tell me. Because if they're inadequate, I'll make changes. But bear in mind that I'm restricting this course for you to the confines of the standard syllabus. Although there are times when I've gone outside the syllabus because I've felt it's easier for understanding. All right, thank you for your attention. I hope you're doing well in your course. Please focus on the drills to see your readiness, and I'll see you back in the next tutorial. Cheers for now. This is Ron, VK2DQ.